Welcome back to Okonko Academy. I would like to recommend that if you are new to this channel, you like and subscribe, and also you put us on post notification so that you always be notified on every new content uploaded. So in the previous tutorial, we talked about partial derivatives and how to find partial derivative with respect to x, y, and other variables, and also we talked about higher order partial derivatives. In this tutorial, we are going to consider the chain rule on partial derivatives. So in our previous lecture, that's calculus 1 and 2, we did chain rule in differentiation. This concept is similar to the one in calculus 1 and 2, but it's quite tricky. So now let's quick start for today's section. So for today's section, we are going to talk about chain rule of partial derivative. Now with partial differential, we always know we deal with functions of several variables, that is function having two or more dependent variable. Those variables could be either x, y, z, any other letter. Now in this diagram here, this diagram is basically termed as the tree diagram. This diagram makes it easy for us to write the chain rule of a particular partial differential. Now let's consider a function z, and that function z is dependent on x and y. So now we have our function here to be z, and that function is dependent on x and y. And now our y is dependent on u and h, and our x is also dependent on u and h. So now the question is, we are to find the partial differential either with respect to u or with respect to h. So now this tree diagram makes it very easy for us to find the partial differential. So first of all, going through the tree diagram, we have our function z, and that function depends on x here and y, and our y depends on u and v, and our x also depends on u and v. So now we can see that the differential of z with respect to x becomes a partial differential. Why are we saying it's a partial differential? This is because our z is dependent on x and y. So therefore, differentiating z with respect to x becomes a partial differential. Okay, now let's consider differentiating z with respect to y. Now differentiating z with respect to y also becomes a partial differential. Why? This is because our function is dependent on x and y. So therefore, we differentiating z with respect to only one variable becomes a partial differential. Now moving on to the function x and y themselves. Those two functions are dependent on u and v. So therefore, differentiating x with respect to u becomes a partial differential. Why? Because our x is dependent on u and v. The same manner, differentiating x with respect to v also becomes a partial differential. Now differentiating y with respect to u also becomes a partial differential. Why? This is because our y is dependent on u and v. In the similar way, differentiating y with respect to v also becomes a partial differential. So now we can see that because their functions have two variables, the differential of one function with respect to the other variable becomes partial because the function is dependent on two variables. That's in this case. So now let's look at how we are going to compress the expressions. That's the expression for the partial differential of z with respect to u and the partial differential of z with respect to v. So now how do we go about it? So find the partial differential of z with respect to u. Now we are going to traverse this part. Now we are going to traverse this part. That's for u. We are going to traverse this part because we can see that, and we can also see that our z traversing this part, we get an expression of the partial differential of z with respect to x, and also we get an expression, the partial differential of x with respect to u. So therefore this part gives us an expression that's del z del x multiplying del x del u. That's the partial differential of z with respect to x times the partial differential of x with respect to u. That's traversing this part. Okay, now we've done that for the x. Now let's do same for the y. So now we can see that when we traverse the path from z leading to, so when you traverse the path from z leading to u, we can see that we are first going to traverse this expression, that's dz dy, and now we also traverse this expression, that's dy du. So therefore finding the partial differential of z with respect to u, we are first going to have this expression, and now we are also going to have this expression. Now this expression is in terms of x and this is in terms of y. So therefore adding these two expressions gives us this whole expression, that's the partial differential of z with respect to u. Now using that same idea to find the partial differential of z with respect to v. So now with the v, we are going to traverse this part. Now traversing this part, we have an expression that is dv dx, and another expression dx dv, giving us this. Okay, now traversing this part in terms of v, we have dv, we have dz dy, and we have dy dv. So therefore giving us this expression. Now having this expression in terms of x and this expression in terms of y, when we combine those two expressions together, we end up getting this equation to be the partial differential of z with respect to v. Okay, so now having understood this concept, we are going to transfer the knowledge from our understanding to solve these two examples, which are very simple. So now with the first example, for us to solve any partial differential, we first need to check the dependent variables, that's the variable the function is depending on. So now in this function we have z, a function of x and y, is equal to 4x squared plus 3y squared. That means that our function z is first of all dependent on x and y. Now with the second equation, we have x, a function of t, and that's equal to sine t, and we have a y, a function of t, that's equal to cos t. So now we can draw a tree diagram for our question. So now with our question we have z, and that z is dependent on x and y, and our y is dependent on t. Our x is dependent on t, and our y is also dependent on t. So now let's write expressions for each of them. So in this part, from z to x, that becomes a partial differential. Why? Because our z is a function of x and y. So therefore, differentiating z with respect to x becomes a partial derivative. Now considering the down one, differentiating z with respect to y also becomes a partial derivative because our z depends on x and y. Now differentiating x with respect to t becomes a direct derivative. Why direct? Because our x is dependent on only one variable, which is t, and our y is also dependent on only one variable, which is t. So therefore, differentiating y with respect to t becomes a direct differential. So now finding the total derivative for this, that's the derivative for z with respect to t, now becomes so we first have this expression, that's dz dx, multiplying the expression dx dt plus the expression dz dy multiplying the expression dy dt. So now, having established this, let's find the partial differential of each of the term. Let's find the expression for each of the term. So starting with the partial differential of z with respect to x. So now from the equation we have 4x squared plus 3y squared. So now find the partial differential of z with respect to x. That means our y become constant because we are not differentiating with respect to y. So therefore, differentiating with respect to x, we are going to end up getting 8x. Now similarly, the partial differential of z with respect to y, making x constant, the first term disappears, leaving the second term, ending up in 6y. With the next two expression, that's dx dt. Now our x is sine t. So now differentiating sine t, we get cos t. Now dy dt. So now our y is cos t. Now differentiating cos t, we get negative sine t. So now substituting these expressions into this, we get our final dz dt to be equal to That's dz dx, which is 8x. Now you have 8x multiplying cos t plus 6y multiplying negative sine t. So now we are not done, because we are finding z with respect to t. So therefore we have to replace the value for x and y. So now we had our expression for x to be equal to sine t. So therefore we have sine t cos t. Now bringing the negative out, we have negative 6. Now our y is equal to cos t. So therefore we have negative 6 sine t cos t as well. Now simplifying these two, we end up getting 2 sine t cos t. Simple as that. Simple as that. Now with the idea from example 1, let's use that same idea to solve example 2. So now with that example 2, we have our function z, and our z depends on x and what y. So therefore here our z dependent on x and y. And now we can see that our x is dependent on u and v, and our y is also dependent on u and v. So therefore we have x dependent on u and v. We have y is also dependent on u and v. So now this is our tree diagram. So now let's write our expressions. From z to x becomes a partial derivative. Why? Because our z is dependent on x and y. That's two independent variables. So our z with respect to y also becomes dz dy. Now the expression up here becomes dx du. Now the expression down here becomes dx dv. Now similar one, we have dy del v. Now we also have del u, del y, del u. Why having del x, del y, del y? Because our x and y also depends on two variables, that they have two independent variables. So therefore our derivatives are also going to be partial. Now we have to find the partial derivative with respect to u and y. Now starting with the first one, that's partial derivative with respect to u. So now we already have this expression here. That's our partial differential of v with respect to u is given by this expression. So therefore our main task is to find dz dx dx du, dz dy, dy du. That's very easy to evaluate. So now, first of all, we need to go back to our expression. So now our expression was given as z is equal to 3x squared minus 2xy plus y squared. So now, finding the partial differential of z with respect to x, that's we are maintaining y, making y to be constant, so therefore this part goes away, becomes 0. Now differentiating 3x squared gives us 6x, and differentiating negative 2xy with respect to x gives us negative 2y. That's very good. Now let's perform partial differential of z with respect to y. Now the partial differential of z with respect to y, also our x becomes 0. Now differentiating negative 2xy, we end up getting negative 2x, and now differentiating y squared, we end up getting positive 2y. Okay, now let's find the partial differential of x with respect to u. So now with the x expression, we have 3u plus 2v. Now differentiating with respect to u, that means our v becomes 0. Now differentiating 3u, we end up getting 3. Now differentiating x with respect to v, our u is constant, so therefore our 3u goes away. Now differentiating 2v, we end up getting 2. Partial differential of y with respect to u, same approach. So now we have 4u minus v, so our v becomes constant. So differentiating 4u, we end up getting 4. Now the partial differential of y with respect to v, so now we are differentiating with respect to v, so therefore our u is constant, so 4u becomes 0. Now differentiating, our v becomes, our u becomes constant, so our 4u is 0. Now differentiating v, this has negative 1. So now I have all the expressions here. So now we have to evaluate del v with respect to u and del v with respect to del z with respect to u and del z with respect to v. So now with these expressions, I'm going to tax you all to substitute in the expressions and multiply, then simplify. But you need to take note that in the first expression you have del z with respect to u, so therefore you are going to substitute the function for x and v inside, and with the second one too, you are also going to substitute the function for x and y also inside. So now, my lovely viewers, I'm leaving this one to you as a trial. Just go and multiply each of the 10, then simplify. After simplifying, substitute the function that's the x function and the y function, in terms of u and v, then you simplify. Thank you all for your audience. See you in the next tutorial, which we are going to consider the equation of the tangent and linear approximation. See you. Bye.